Okay, so these are the operations, and we'll see today how we can do these very efficiently. In fact, it'll be very easy to do them in constant expected time per operation. And with a little bit more work, we'll see that we can do all of these things in constant expected time per operation. And actually, this one we can do even better. We can make it worst case constant time. So every search will take constant time. Maybe adding and removing will still take constant time on average or an expectation, but there may be some add or remove operations which take a bit longer. Okay, so let's start with something really basic. Here's a function called h sub a of x. Really, it's a function of two variables, a and x, but it's helpful to think of a as the fixed thing. And it is just, you take a and x, you multiply them together, you take that result modulo 2 to the w, and you divide that by 2 to the w minus d, and this is an integer division, so you take the floor of that. Okay. All right. So what about this thing? Well, the top part, the numerator, is in the range 0 to 2 to the w, but then you divide by 2 to the w minus d, which actually means that the result that you get is in the range 0 up to 2 to the d. Okay. So HA goes from 0 up to 2 to the w minus 1. That's the inputs, but the outputs only go from 0 up to 2 to the d minus 1. Okay. And so in general, if d is less than w, then this is a shrinking operation. It takes you from a big set onto a smaller set. All right, it's easy. What else can I say about this thing? Well, this looks like a sort of complicated formula. There's a mod operation and a division operation, but actually it's not complicated at all in languages that are close to the machine in some sense. And in particular, in the C programming language, the code for this looks like you take A, you multiply it by X, and then you right shift the result by W minus D. Right, so what happened to the mod operation? Well, we don't need to do it because by default, integer arithmetic is done modulo 2 to the word size on just about every computer that I know of. So that happens for free, and division by a power of 2 is just a right shift operation. So this is a really short thing. Neither part is expensive. Right shift is really trivial. Multiplication is slightly more complicated, but both of these are extremely fast on modern processors. All right, why am I interested in this function in particular? Well, that's because there's a theorem or a lemma about these things that's due to somebody who works a lot on hashing, Martin Dietzfeldbinger. And it's buried inside a more complicated paper, I think from 1996. But in here, this hash function appears, and there's a nice, sort of nice result, which is if x, y are in, well, the range we're interested in, 0 up to 2 to the w minus 1, and x is not equal to y, then what will I say? The number of values a that we can use here in this set 5. Okay, so I'm going to count the number of odd integers in the range that I'm interested in, that are my choices for A, which cause the hash value of x to equal the hash value of y, where x and y are any two distinct things. That is less than or equal to 2 to the w divided by 2 to the d. Okay, that's not so exciting, or maybe it's exciting or not, but what does it mean? Why is that useful for us? Well, the consequence of that is that if we take a random A, so random odd integer A in this range, then the probability that the hash value of x is equal to the hash value of y, well, this is the maximum number of A's which could make that happen, choices of A which could make that happen, and the number of choices we have for A is 2 to the w minus 1. So you take this thing, divide by 2 to the w minus 1, and you're left with 2 over 2 to the d. Okay? So let's think about this for a bit. We have this big set over here of size 2 to the w. Those are the inputs to this hash function. It maps it down onto a small set of size 2 to the d. And if I take two different values over here, x and y, then, well, x goes somewhere. And if this was really a truly random function, then y would pick a random thing over here as well. And the probability that it would pick the same thing that x picked would be 1 over 2 to the d. Well, this says that's not quite what's happening. It's not quite that perfectly random, but it's pretty close. The probability that x and y go to the same place is only 2 over 2 to the d. So it's maybe twice as much as you would expect from a random thing, but not bad. And not bad because all we need for this hash function is to pick one random integer, and we get this nice hash function with this property. Okay. All right, so let's remember that, and I will do a couple of things. So in general, we're going to have this set over here, well, of all the integers that we can store, and we'll be mapping onto some smaller set. And I don't want to have to write 2 to the d everywhere for the rest of the class. So I'll just say now m is equal to 2 to the d.
Pat?
Yep.
So is A then the key in the hash table?
A is, I mean, the way it's described in the literature is what you're doing is picking a function from this set of 2 to the w minus 1 functions at random, but what all that means is you're picking a at random. So I don't know what you want to call it. It's just it's completely, once you've picked a, it completely defines your function h of a. So it's you can think of it as the hash function that you're using for your table.
Okay, thank you.
Okay, good. So let's just remember for x distinct from y, the probability that HA of x equals HA of y is less than or equal to 2 over m. Okay. That's what I want you to remember from there. And, you know, in terms of a practical perspective, remember also that this particular hash function is very efficient. There's nothing terrible happening there. I wish more programming language creators knew about this, but because you find all kinds of bad hash functions in programming language implementations when this would be better and faster. Okay. All right. So let's see how we could use this. Yep. What is wrong with even numbers? Well, this lemma is not true if you take a to be a random integer in this whole set. So in particular, there will be, so a bit of a historical remark. The hash function was noticed well before 1996, like 20 years before that, you know, it's a nice and efficient hash function. But the problem is there are values x and y, so that if I pick a random a, which could be odd, could be even, then the probability that HA of x equals HA of y, if I choose a to be not necessarily odd, is it can be actually w over 2 to the d, and w is not constant, right? W is this, I mean, w is at least log n, for example. So the even numbers are bad for this hash function. What's that? If a is even, then the hash value is always even. And so if a trails, well, no, that's not true. If a is even, the hash value is not always even, because the hash value only uses the highest d bits of the product, and that could be even or could be odd. The result of the multiplication will always be even. But you're kind of seeing what that means. If a ends with a whole bunch of zeros, then that product ends also with a whole bunch of zeros, and maybe some of those zeros bleed into the part that you're keeping, those d bits that you're keeping. So that already says at least some even numbers are really, really bad choices. Like 0 is an even number. That's a very bad choice for the thing to multiply by here. Then everything goes to 0. Okay. Yeah, so it has to be odd. And so that's the main thing. The contribution of Dietz-Filbinger is he noticed that if you just restrict yourself to odd things, suddenly it works. Before that, without that, it doesn't. And before this, there were lots of other hash functions with this sort of property up here, but they were all more complicated. And they did things like, I mean, there was a similar flavor, multiplication and then a mod operation, but the mod operation was often by a prime, which doesn't have an easy way to implement on a computer. So it's not just, well, I mean, it's hard to get it cheaper than for free, which is what happens in this operation. Okay, so let's see how we can use this to do, let's say, the most basic kind of hash table, which is the following. So I'm going to take n elements, so some s, which is a subset of the integers that so it's the integers that I want to store, and I'm going to put them into a table of size m, right? So everything in my set will use this hash function to pick a slot in the table. So this is of size m. And, well, sometimes it will happen that two or more elements pick the same slot. You get 3 here. And when that happens, or in fact all the time, the elements that pick this, I don't know, let's say x1, x2, x3, x4. The elements that pick the same slot go into, let's say, a linked list. So here you have a list with x2 and x3. Here's a list with x4, x5, x6. Okay. So this table is of size m. And I'm going to say the size of S is n, number of elements you're storing. And I'm going to say ni is just going to be equal to the number of elements in your set which end up at position I in the table. So that's where HA of X is equal to I. So I have n elements, they're split among these m table entries, and ni just tells you how many are in table location I. And I don't know, you can sort of see that, well, on average, the number of elements in a table slot, and I don't mean average in terms of probability, I just mean average, like you add them all up and divide by the number of table slots, it's going to be n over m, right? So that's the average number of things per table slot. And, you know, we'd like to then say, well, we're going to pick m, so it's about the same as n. So on average, we get these lists of constant size. Now, average is a bad thing to use here because even if I take all of them and put them in the first table slot, then there's one table slot with n things, but there's m minus 1 with 0 things. So the average is still n over m, but that's obviously not a good strategy. So we need to be a little bit more clever about this. So let's say, I mean, here's an easy lemma. For any x, and I'm going to stop writing in this set all the time. X and y are always going to be in the set of integers that we're looking at. For any x, let's say, and actually let's even say, even better is we'll say Si is the set of things that go to table location I, and I is going to be the size of that set. So for any x, whether it's in S or not, how do I want to write this? The expected size of S sub HA of X minus, not counting X if it's in there, is less than or equal to 2n over m. Okay. So you give me any x. It doesn't matter if it's in the set here or not. I hash x and I go and I look at where x would go if it was in here. There's a set of things that is there. I count them all up except for the one that may be equal to x or not. And the expected size of that thing is only 2n over m. That's really easy to see. Why is it really easy to see? You just define this indicator random variable ixy, which is just equal to 1 or 0. It's 1 if HA of x equals HA of y, and it's 0 otherwise. Then the size of this set S sub HA of x minus x, that thing is just the sum over all the y in S minus x of this indicator random variable ixy, right? This variable just counts as a 1 if x and y have the same hash value and 0 otherwise. So if I want to know how many other things end up in the list that x would choose, well, you just add up those indicator variables. And that means their expected values are the same. And you use linearity of expectation to bring the expected value in. Now, Rxy is just asking, I mean, the expected value of that is just the probability that HA of x equals HA of y. And x and y are different because that's what the sum is over everything in S except possibly x. So the probability that this thing is equal to 1, which is equal to its expected value, is only at most 2 over m. Okay. So that's less than or equal to that sum, 2 over m, and that sum has at most n values in it, so 2n over m. Okay. It either has n values or n minus 1 values, depending on whether or not x is in the set. Okay. Good. So that's nice. That gives us what we want is not the average size of a list, but if you fix a particular thing, what's the size of the list that you would have to look in to search for it? Well, it's only 2n over m, or the number of things in that list other than x is only 2n over m in expectation. All right, so that basically does just about everything we need. So I will say that this is equal to O of 1 as long as m is in omega n. Okay. So as long as m is not much smaller than n, then this is going to be at most a constant. And we'll see, actually, you can even crank it up a bit and this is true even if you take m to be really big, in which case you can send this thing close to 0. So let's write that down. It's important. That's the expected size of the set HA of x minus x is less than or equal to 2n over m. All right, so then we're laughing. What are the operations I want to do? I want to add, remove, and find. First, let's look at find. If I want to go searching for something, the x, I take the hash value of x, I go directly to the table location that stores that hash value, and then I say, just look through the list. And the expected length of that list is going to be at most 2n over m. If x is not there, and it's going to be 2n, at most 2n over m plus 1 if x is there. So, and as long as I keep m and n the same size, then I get a constant expected time to do find. And adding and removing is the same sort of thing, right? To add something, I go to the list and I append it there. To remove something, I go to the list and find it and then remove it from the list. It's all really easy stuff. It all just depends on the length of the list, and the expected length of that list is always this 2n over m or 2n over m plus 1, depending on whether or not x is there. And then the only sort of trick, but we know how to deal with this, is to make sure that n and m are always close enough. Let's say they differ by at most a factor of 2. And well, we know lots of tricks for that. You just make sure that, let's say, I mean, it's easy to guarantee something like m is going to be at most 3n and at least, I don't know, n over 2, something like that. And whenever that gets violated, like, if you get too many values, so you add too much stuff and this isn't true, then you do something like double the size of m. Yeah, so this is the standard amortization sort of trick for keeping an array, growing an array when you need to. All right, so that was too easy. And it's the kind of thing you see in the introductory data structures course. If they cover hashing at all, that's usually what you'll find. Now, what if I would like to guarantee something stronger? This, what I just described, is called hashing with chaining. And it's O of 1 expected time for all operations. And O of n space, because all you've got is one table of size m, which is roughly the same as n, plus these lists, but the total length of all the lists is only n. So that's good. What if we want to do better and say, I'm willing to do, well, let's say I'm even going to give up add and remove for now and just focus on being able to store the set, some fixed set, without changing it, so that I can do this in constant worst case time, so that no matter what I search for, I never have to spend more than a constant amount of time. This structure does not have that property. In fact, this structure will have a list, actually with high probability, there will be a list in here whose length is at least log n over log n. So there will be searches that take they're nearly as slow as they would be in a binary search tree. Okay, so let's do that. So now it's just a fixed set S of n values. And I want to be able to do this find operation in constant time. All right. So what does that mean? Or how could I hope for that to work? Well, it sort of means I want to do the same thing here, but I don't want to have these chains. I don't, when I hash X and I find it somewhere, I'll either want to see X there by itself or nothing there, because X is not in the table. So I'm looking for a hash function which doesn't have these sort of things here, 2 things hashing to the same table location or 3 things to the same table location. Those are called collisions. And so I really want that these collisions never happen. So there's no 2 values in S. So what I'm looking for is no X not equal to Y with XY in S such that HA of X equals HA of Y. Because if I have 2 values like that, that means they have to go to the same table location and they have to get stored in a chain. And if I have 2 values like that, maybe I have 3, maybe I have 4, maybe I have 100. So I want all those to go away. Well, the hash function doesn't guarantee that. So how can I still get that to work? So, well, the hash function guarantees something. It says for any X, if I look at the table location where X is stored, the expected number of things that is different from X is 2n over m. And I said, well, that's at most a constant. But we could make that much smaller than a constant. So we could say, well, let's just expand from here. So we don't want any X not equal to Y, both of them in S, such that this is true. So another way to say that is that I will look at the following thing and hope that it doesn't happen. So I'll go over all the X's in S. I'll go over all the Y's in S except for X. So this is going over n choose 2 different values. And what I want is that the indicator variable, I, X, Y, well, I'm worried that it is equal to 1. Okay. So I'm worried that this is equal to 1, because if this is equal to 1, it means these two things have the same hash value. I want to avoid that. So the event that I'm going to look at is over all the x's and all the y's, is any of these things equal to 1? So this is an OR over all these n choose 2 things. And I'm interested in the probability of that, right? So if any two hash values have the same, any two elements of S have the same hash value, then this is a event that you consider to be true. And so I have the OR of a whole bunch of different events. And one thing that, well, you may or may not remember is to get an upper bound on the probability of that, I can just sum all the individual probabilities. Okay. So that's less than or equal to the sum over X, Y, the probability that I, X, Y equals 1. Okay. Well, this I know, or at least I know an upper bound on it. That's just less than or equal to same double sum with X and Y. And what did we say? 2n over m. Sorry, not 2n over m. No, just 2 over m. That's this thing up here, the probability that those two things are equal. So this is a sum of n choose 2 things, all of which are the same. So this is equal to n choose 2, 2 over m. N choose 2 is n times n minus 1 divided by 2. There's a divided by 2 and a multiplied by 2, so those will go away. So this is n times n minus 1 over m. To make things simple, let's say this is at most n squared. Okay, so I have this crazy bound that says, well, if I shove everything into all these n elements into this hash table, then the probability that that I have a pair that collide is at most this thing, which seems crazy, right? This is much bigger than 1 typically, but this is true for any n and m. In particular, if I take m equal to 2n squared, then this is less than or equal to half. Right? In fact, for any m bigger than or equal to 2m squared, then I'll get this thing to be less than or equal to a half. So this hash function can be collision-free if I'm willing to use a huge table. So if all I care about is that these find operations run fast, well, if I'm willing to use a table of size n squared, then yes, there's a good chance that I pick my hash function and everybody gets their own table slot. And if that doesn't happen, well, I can just pick another hash function and try again. Okay. And on average, I mean, the first one has probability half of having this property. If it doesn't, then I pick another one. It also has probability half of having this property. So on average, I might have to pick 2 hash functions before I find one that has this property for this particular set S. Okay, well, that's not so exciting because I need such a big table here. By the way, does this does this look familiar in any way? There's a so what am I asking? I have these n things. They all get some hash value that's kind of random, and I'm kind of asking, what's the probability that no two of them have the same hash value? Is there a sort of common example in math and probability that talks about this situation? What's that? What? Yeah, balls and bins, but in common language, it's people talk about the birthday paradox. And in the birthday paradox, it says if you have m birthdays and more than square root of m people, then you're likely to have two with the same birthday. Okay. And that's assuming that birthdays are somehow uniformly distributed. And so this is just saying, yeah, and if I have, right, so m is the number of different days on which people could be born, n is the number of people, and if the number of days on which people could be born is bigger than n squared, then there's a good chance everybody gets their own birthday by themselves. So that's what's happening here. So it's kind of what you would expect to happen if this was a truly random function, at least within a factor of 2. Okay, all right, hashing with chaining. So let's remember I will write that up here. As by saying the probability of no collisions, meaning everybody gets their own table slot, is bigger than or equal to a half, but that's only for m bigger than or equal to 2n squared. Okay. Nice to know, but not satisfying from a data structure perspective. We don't want to spend that much space. So let's do something completely unexpected, unless you've seen it before. And let's look at this thing. Back to this table where the size of the table is linear size. And remember, Ni was the number of things in table slot I. So let's sum over the table slots. So if I take this sum, it's just going to be n. So just the total number of things stored there. But I'm going to take this sum squared. I'd like to know something about that. So now it's a random variable because it really depends on it changes depending on how things are sent to the table slots. So for instance, in the case where things work out perfectly, where you have exactly the same number of elements in each table slot, then it's going to be something like n over m squared for each of those terms. So that's the sort of typical table slot. Then you square it, and then the number of those terms is m. Well, this is a constant. So this would then be a constant times m, and m is a constant times n. So this whole thing would be a constant times n. So that's one end of the spectrum where things are perfectly balanced out. At the other end of the spectrum, all of the n elements go to table slot number 1. in which case you have one term here which is n squared, and all the other terms are 0, which isn't good. I mean, I don't know if that's good or not. It's just telling you that this sum varies somewhere between n, or constant times n, and possibly all the way up to n squared. So let's try and analyze it. And the right way to do this, or one way to do this, is to rewrite it in a different way. So I claim that this sum is equal to this sum. So why is that? So let's say I go to table slot I. Well, not tables, I go to some table slot. And there's a bunch of things in that table. Okay. Now, this sum goes over all pairs of things in my whole set. And in particular, it goes over all pairs of things in this table slot. Okay. And for these guys, the answer is 1. They're both in the same table slot. Okay. So I take every pair in here, and each pair in this one table slot will give me a 1. And it's not even just every pair, but I also sometimes I have x and y both equal to the same thing, so they contribute theirs as well. And so that the point is, in this sum, this particular table slot contributes exactly ni squared. For every 2 elements here, including when I take the same element twice, I get a 1. And how many pairs are there in the set of size ni? There's exactly ni squared. So these two things are exactly the same. Why would I want to do this? Well, I want to do this because I would like to know the expected value of this thing. And I have some hope of computing the expected value of this thing, but not quite there yet. This is a bit annoying because it also has things in it where x and y are the same. So let's get rid of that. So how many things are there where x and y are the same? Well, there's exactly n of them. And in that case, h of x equals h of x. I mean, that's always true. So if I get rid of those ones where they're the same, then there's going to be n things. And now I can take the sum only over the ones where they're different. So that's where y is in the set, but it's not equal to x. Okay. All right, so now we can do what we did before. So we've got an n. This thing is 2 over m. The probability or the expected value of this thing is 2 over m. So 2 over m. And the number of things in here is, and choose 2. So what is that? That is n plus the 2's disappear. There is an n squared on top over m. Well, this looks good now because this is just, well, let's say that this is less than or equal to, or let's be really vague about it. This is O of n, provided that m is at least a constant times n. Okay. So if I were to take this table, the original one that I made, and sum up the squares of the sizes of the lists, then I get something whose I get a sum which is only linear. It only adds up to O of n. Okay. So let's write that down. And that's for M. Okay. So there's a few facts written up here. And some of them, this one is useful when M and N are about the same. This one is useful when M and N are about the same. This one is only useful when M is much bigger than N. So does anyone see where this is going? So the original structure I presented, what's that? I don't. A little bit, but so what did I? So this here actually tells me if I'm willing to spend quadratic space, then I can answer the queries in constant time, right? Because if I'm willing to spend quadratic space, everybody gets their own slot. This thing here tells me that, right, so I have this structure, this one is talking about this original structure here, where at each location I stored a list. But instead of storing a list, it's saying I can afford to store something much bigger than the list that's here. I can afford to store something that's the square of this thing. Okay. So right, in this case, there's two things here. But this is saying, well, I could have stored some structure of size 4. In this case, there's 3 things here, but I could have stored a structure of size 9. And even if I did that, when I add it all up, I would still only get something whose expected size is linear. So what you're going to do is use a table of size M, which is proportional to N. Each element in that table is not going to be a list. So if I look at position I in that table, it's going to be a big thing. And its size is going to be 2ni squared. We'll call that mi. It should be at least that big. Okay. So when I go searching for x, I hash it into this some location in here. And then I have a table that stores all of the things that have the same hash value as x, including x, but it's storing them perfectly. So now I hash x into this table, and either I see x there, in which case I'm happy, or I don't see x there, in which case I know x is not in the set. Okay. So, and so that's the structure. It's the same structure we started with, hashing with chaining, but you replace these lists by quadratic sized hash tables for the elements that are in that list. And this result here says, yeah, that's fine. Even when you add up the sizes of all those quadratic sized hash tables, you get something whose expected size is linear. Yep. Well, so we're talking about just storing, for now, just fixing the set S that we're going to store. We get all the the n elements in advance, and we're going to build this structure. So here's how, I mean, just to be really specific, here's the algorithm. So this is given S. So first thing you do is, let's call that step 1. You pick, well, let's say we, big set S, we're going to say, let's take M, that's fine. Pick a random A and one of those odd guys up to 2 to the W minus 1. So once I've done that, so I know everything in S, I pick my hash function, I can go ahead and compute now these numbers, n1 up to nm, right? That's just use an array of size m, and then each time you set it starting with all zeros, and now hash each thing and go and increment the value that's stored at that location. So now I know n1 to nm. Compute the sum of the ni squareds. If I know the ni's, I can compute the sum of the ni squareds. And if that sum is bigger than or equal to, I don't know, put your favorite constant here, 42. If that's bigger than or equal to 42n, then go back to step 1 or step 2. So that just means you picked a bad A, go try again. Okay. Yeah, okay. So, and if you pick this number 42, right, then the probability that this happens is going to be less than a half. Let's say that's a reasonable thing. In fact, you only have to pick something that's, we had computed this expected value fairly precisely. You just need to pick a threshold which is twice that expected value in order to make the probability of this less than a half. All right, so otherwise you get past this step. For each I equals 1 to m, create a table of size n, what did I say, 2ni squared. So do that. Not only do you create the table, you pick a random AI. That's going to be the hash function that you use for that particular table. Now you've got, you know what you want to store in that table. So yeah. So you know what it is you're going to be storing in that table. So now check, if let's say if HAI has a collision for the set SI, remember the set SI are the set of things that get stored at that table location. then, then pick a different AI. This says the probability that you'll have to pick another AI is at most a half. So after picking about 2 on average, you'll find one that is collision free for that little table, and then that's it. So by the time this all finishes up, you will have built this 2-level hash table where any query can be answered by hashing into the first table and then hashing into the smaller table that's stored there. So from step 5 to step 2. So this, all right, it's gone now, but we had actually given a precise upper bound on this sum of these ni squareds, right? It was n plus n squared over m. So this 42, you replace that. I mean, this 42n, you replace that with 2 n plus n squared over m. So 42n is really, this is the thing you use. Now, this is twice the expected value, and there's a well-known inequality called Markov's inequality for these things that says the probability that a random variable, a non-negative random variable, is more than twice its expected value is at most a half. So at each time you pick one of these things with probability at least a half, it works, which means you expect to have to do this twice before finding one that works. And then the same thing happens. Here. For each little table, you expect to have to pick, to try 2 different AIs till you find one that works for that little table. Okay. And well, if you didn't have to do any of that trying again, then it's clear that this runs in linear time, right? I mean, all this stuff is easy. It's just loops. This one, this part here, I guess the hardest, or the part that was not obvious beforehand, that you have to create all these little tables of this size 2ni squared. But by the time you get here, you've already guaranteed that the sum of 2ni squared is also only proportional to n. Yeah, and then you do this. Okay.
Pat?
Yep.
Sorry, just so when we are we doing this algorithm when we're adding elements, or also
So
doing it when
for now, just pretend that you know all the elements in S in advance. You only want to store them. You're never going to add and remove. And if you have that, then this is the algorithm that builds the table for you.
Oh, okay.
We'll see in a second how you get to a structure that allows you to add and remove. Okay. So this result is due to 3 famous people: Fredman, Komlosh, and Semiretti. And it's called perfect hashing. And perfect kind of means that, well, perfect means no collisions. So everybody gets their own location by themselves. So, and that's true, but it happens in sort of 2 stages. But it works. Okay. And this original result was only for static set of things. At least that's what was written in the paper. So a few years later, another group of authors wrote a paper called Dynamic Perfect Hashing. In which they showed how to take the same structure but allow you to add and remove things. So the add and remove operations take constant expected, and amortized time, but the searches still take constant worst case time. So it's basically how to maintain this table. So that happened about 10 years later that this paper appeared. But actually, this guy Fredman, data structures is his thing. He teaches a data structures class, graduate class every year at Rutgers. For the 10 years prior to that, he'd actually been giving that as an assignment in his data structures class. And we'll see, the extension to making this dynamic is you basically just look at the things that can go wrong, and when something goes wrong, you do the obvious thing to fix it, and that just works out. So let's.
So I have a question, and it's a little bit off topic, so I'm not sure. But
Yep.
Could this somehow be related to the second question on the assignment, in which we were supposed to create random numbers in constant time using a database, a data structure of size ON?
I mean, only vaguely related in the sense that to answer that question, there's a thing that's like a hash function, but all you do is divide by an integer to get a table index. So that's a little bit like a hash function. So you have this, I forget, I think it was W was the range of integers that your random number generator gets. So you take one of those things and you divide it by n, I guess, and use that as a table location. So if you think of division by n as a hash function, then yes, it's kind of a simple hash function. But there's nothing for that function, for that question. There's none of this issue of avoiding collisions or things. So you certainly don't need to know this stuff to answer that question. Okay, so what can go wrong here? What are all the things that we need to make this work? So things that can go wrong. Well, here's an obvious one. So we have M, which is the size of the first, the main table here. And for this stuff to work, we kind of said M has to be bigger than some constant times N. That shows up certainly for this thing. So, well, here's something that can go wrong. One is that M, or let's say N, gets too big. Let's say, for example, N is bigger than or equal to 2M. Something else that can go wrong is N gets too small. Maybe N is less than or equal to M over 3. So those are sort of things that can go wrong because all this analysis sort of assumes N and M are close together. But this kind of thing we know how to deal with. Right, when this only goes wrong because somebody has added or removed too many things from the structure. And we know sort of standard trick is Well, we can deal with this by just rebuilding the entire structure whenever one of these things happens. And that amortizes out over the number of operations it takes to make n get so big or so small, because n only increases or decreases by 1 for each add and remove operation. Okay, so when these things go wrong, you just do a global rebuilding, meaning you now know what the elements are, the set S that's currently in the structure. You run the algorithm I just described to build the structure from scratch with an appropriately chosen value of m, so that it lands nicely in between these two, this being too big or too small. Okay. Here's another thing that can go wrong. The sum of I equals 1 to m of ni squared, that gets too big. And I will say 42n, but this is a joke. This just means bigger than some big constant times n. And all right, so if that happens, that means that the number a that we're using in our hash function is a bad choice for this set of things, the set of things that we're currently storing. And there's not much we can do about that, because I mean, that controls, I mean, everything uses that a, so all we can do is the same thing. If this happens, we just have to rebuild the whole table again. Pick a new a and rebuild everything from scratch using exactly the algorithm I described. Okay. Another thing that can go wrong, now this is at the local scales, you get something like ni gets too big or too small, and that's compared to mi. Because remember, ni, well, so mi should be somehow, you know, a constant, some constant times ni squared, right? So it should be mi and ni squared should be about the same thing. And, you know, it can be that I start adding things to the table. I had this thing here that was working nicely for a while. It had size, I don't know, maybe 2 ni squared. But now I added something that needs to go in here, and now ni squared got bigger, and yeah, so I'm trying to put too many things in this table, so that this bound here, this probability of no collisions, isn't guaranteed anymore because I'm not satisfying this requirement. But again, this is the kind of thing we know how to deal with. So if that happens, that means too many things got added to this table since the last time I built the table. I can afford now to rebuild it again, but this time with a bigger size, so a bigger value of mi. And similarly, if you start deleting things and a whole bunch of stuff in this table disappears, so that it's really much bigger than necessary, well, you can afford at some point to rebuild it from scratch. And again, that amortizes out over the deletions that went inside this little table, or the additions that went inside this table. So that's no problem. That's just a local rebuild. And then finally, the last thing that can go wrong is locally, you get h of ai is not collision free for SI. So that's this picture again, but the problem is not that this table is too big or too small, but it's that you just added something, and when you hash it using the hash function that you're using for this table, it goes in, I mean, it wants to go someplace where there's already something there. And well, not much we can do there. Well, what we'll do there is just pick a new hash function and then rehash everything into the table. We may have to do that a couple of times until we get one that works. But as long as, well, because we've already made sure this isn't the case anymore, the table is the right size to store this number of things. The only problem was that we were using the wrong hash function, so the wrong AI. Picking another one, we may have to pick a couple of them, but eventually we'll get there. Okay, so this stuff and this stuff, this is all really standard analysis. There's nothing to worry about here. These two things, they look weird somehow because they're these probabilities and they're talking about different sets of things. But here's the way you look at these things. So you imagine breaking time up into to periods of time. So every once in a while, you have to do a global rebuilding because, let's say, n gets too big or too small. But between two of those global rebuildings, the value of n is in the right range. Now, during that range, the elements that are actually stored there might be changing, right? I can delete one thing, add another thing, delete one thing, add another thing. But just look at, let's say, the first, so in that range, look at the first m operations that are add and remove and so on. So there was a rebuild. After the rebuild, there was a set S of size n. You had a nice table for it. Everything was the right size. Then a bunch of add and remove happens. And in total, that means that you had all the things in S were in the table at some point, and all the things in S prime, where S prime is this stuff that you've that was, let's say, added in here. So S and S prime, well, if there's only m of these operations, then, well, they're both about the same size. They're both about the size of m. And as long as this condition here was true for everything in S union S prime, then you would be, nothing would happen in that sequence of m things. There would be no rebuilds. Well, and the probability actually that that it was this condition was satisfied is actually here. Well, we had it. If you pick this constant right, then with probability of half, this table would have worked even if all I did was store all of these at the same time. Okay. So anyway, the point is that over m operations, you expect that possibly you'll have to do some rebuilding because of this, and the rebuilding will happen twice in expectation. So the expected number of rebuilds there will be a constant, 2 in this case. And so you amortize that over those operations. And then finally, the same situation here. If the size of this table is right, but I keep adding and removing things to it, then look at the first 2 ni things that were added and removed. The number of times you'll have to pick a new hash function for this table, the expected number is only 2. So it's really, it really is an exercise of just carefully going through this and counting things. And now you can do add and remove operations in constant amortized expected time, and find operations in constant worst case time. All right, and now we are over time, so we'll stop there. I can maybe answer some questions until people from the next class arrive.